Hello everybody, we're going to be talking about Chapter 9. This is our last new section in this course. This is on hypothesis tests for one population mean. Now in the previous chapters, especially in everything leading up through this chapter, we've talked about the ideas of collecting samples. We've talked about the ideas of finding those characteristics of the sample that we want, which is namely the mean, standard deviation, and so on. We talked about distributions and types of distributions, and we talked about the normal distribution. We talked about probability. We talked about the idea of being able to take the mean, the sample mean, the sampling mean of the sampling distributions in Chapter 7. And then in Chapter 8, the last chapter, we talked about confidence intervals. Well, now the logic is going to come full circle. So this is where we bring everything together. And this is very important to us. So in this case, we're going to talk about the nature of what hypothesis testing means. And the way that we want to talk about this here is, let me just sort of set the stage. I'm going to put these terms up here because we need to know this one. But suppose that the mayor of Providence comes to the microphone and says that the mean income of Providence, in the city of Providence, is $50,000. Now, we can actually, that's a claim that we can test. That's a claim that says, well, it might be $50,000. It could be close to $50,000. But how close is close? How can we statistically come to the conclusion that the mayor's right if the mayor's, let's say, $100 off? Would we say that the mayor's wrong? How about $1,000 off? How about $2,000 or $10,000 off? How far is too far? Well, the logic here is that if we're testing, what we're going to do is we're going to make a claim. A claim like the mean income is blank. And we call that claim a null hypothesis. That's a hypothesis to be tested. It's a claim. It's a guess. Somebody comes along and says, well, maybe it's an educated guess anyways. But it's a hypothesis to be tested. Based on the information, what could we say about that population? We have, along with this null hypothesis, which is our statement, an alternative hypothesis. Well, what if we're wrong? What do we say then? An alternative hypothesis is a hypothesis to be considered as an alternative to the null hypothesis. So we use some symbols here. We use H subscript 0 to represent that null hypothesis. And we use H subscript A. Sometimes we use H subscript 1. It depends on the textbook that you're using to represent our alternate hypothesis. And then our hypothesis test is the problem of a hypothesis test to decide whether or not the null hypothesis should be rejected in favor of the alternative hypothesis. And our null hypothesis, what we're really looking to see right here, is whether or not that claim is correct. So if we're talking about our mayor making the claim about $50,000 being the mean income, the average income of the city of Providence residents, then that is our claim. Our alternative hypothesis might be, well, we don't know whether it's higher or lower, but let's just make an alternate hypothesis and say it's not $50,000. We need a test to figure out whether or not we should reject that claim and how far we would want to go. All right. Well, if we were making this claim, we also want to be aware that we could be making an error ourselves. If we are statisticians, it is quite possible for us to make a mistake. What kind of errors can we make? Well, we could reject that null hypothesis when it's in fact true. We could reject the mayor's claim of $50,000 when it turns out that the mayor was right all along. This type 2 error is that, well, we fail to reject the hypothesis when it is in fact false. It's a little bit of a different false. I know that seems like it's sort of the same game, but really we're doing something different, right? Let's say we don't reject that null hypothesis. We accept what the mayor says, that it's $50,000. When in fact, it wasn't $50,000, right? We call that a type 2 error. We're going to concentrate in this section, when we do our work, we're going to concentrate on just finding out something about that type 1 error. And we're going to figure out, well, how likely is it that we can reject that null hypothesis when it's in fact true? That's what we're aiming. The type 2 error is a little bit more difficult to quantify, and sometimes it's left for higher level courses than the ones we're taking here. We also wanted to identify something called a significance level. Remember that in Chapter 8, we talked about the idea of a probability associated with our confidence level. We were 95% confident, we had a 90% confidence level, and so on. Well, the probability of making a type 1 error, that is, of rejecting the true null hypothesis, is called our significance level, alpha, which is the same alpha that we had with our confidence level. So in a way, what you're doing is we're applying what we just learned in Chapter 8 about confidence levels, and we're saying, well, let's figure out what probability is associated with that significance level from our confidence interval, and see if we have enough evidence to reject based on that. So that's the logic that's going on right here. For a fixed sample, the smaller we specify the significance level alpha, the larger the probability of not rejecting. So what we're saying right here is that, well, if we make a type 1 error, the probability, the smaller the probability of our significance level, the larger the probability of not rejecting a false hypothesis. So there is a sort of a inverse relationship right here. Again, we're really looking at our type 1 errors when we do our tests, but it's good to know that, well, yeah, there is that relationship between our type 1 and type 2 error probabilities. So what do we do? The possible conclusions. Suppose that we test a hypothesis test, that we do a hypothesis test in a small significance level, right? We say 5%, 2%, 1%, right? If the null hypothesis is rejected, we conclude that the data provides sufficient evidence to support the alternative hypothesis. And if the null hypothesis is not rejected, we conclude that the data did not provide sufficient evidence to support the alternate hypothesis. And this seems like a strange thing to say, but the logic here is kind of like the logic that we use if we're a jury. If we're a jury in court, we're not saying the defendant is guilty or innocent. What we're doing is that we have the presumption of innocence in a courtroom, and if we have a criminal trial, we're either going to find enough evidence to convict the defendant of that criminal offense, or we're not going to find enough evidence. So we exonerate them because we don't have enough evidence to hold them. We don't say they're innocent. We just say we don't have enough evidence, right? And that's the way that we conclude this thing, right? Basically, we're saying one of two things. Either we reject the null hypothesis, or we fail to reject the null hypothesis because we don't have enough evidence. If the mayor makes the claim that the average income in the city of Providence is $50,000, either we do our test and either we reject that claim, claim that it's $50,000, or we just fail to reject it. We just say that we're going to kind of hedge our bets here. We don't have enough evidence to say that the mayor is wrong, right? So that's the hypothesis logic right here. We're not really saying true or false. We're just simply saying that, well, we don't have enough evidence to show that that's wrong. All right, so here's a question. Let's say, suppose we're considering a hypothesis test for a population mean mu, like our mayor. In each part, express the alternate hypothesis symbolically and identify the hypothesis test as either two-tailed, left-tailed, or right-tailed. Well, let me explain what that means right here. But essentially what we're saying is this. We're going to make a hypothesis test. So what we're saying is that... Let me write this out right here. Get my pen going. Hello, pen. All right. So we want to test a hypothesis. We want to test our hypothesis H0, and we're testing the mean for, let's say, what our mayor said, right? We say, well, then the mean population, right? We use mu for the population mean is $50,000, right? Okay. So what do we mean? Well, let's say we want to decide whether the population mean is different from the specified value. We call this, by the way, this value mu sub 0. So what we're saying is that the hypothesis, the null hypothesis, is equal to some specified mean, and that's our specified mean, $50,000 in this case. So if we're just saying that it's different, what our alternate hypothesis symbolically is going to be written as, well, the mean is not $50,000, right? So we would try and make a test so that we're going to say, well, if we test this, we find the mean is not $50,000 when the mayor's wrong. Now, let's say that somebody's arguing from the standpoint of we need more welfare services in the city, and so we're trying to prove that the mayor's claim is not only incorrect, but the actual mean is less than the claim of $50,000, right? That might be the political context. So what do? We say, well, our alternate hypothesis then should be stated more like this, that the mean is less than $50,000, right? On the other hand, if we want to decide whether or not the population mean was greater than the specified value, right? Somebody on the other side of the spectrum comes along and says, no, everybody in Providence is doing great. They're getting way more than $50,000 is the mean, right? So we're going to say, well, then the mean is greater than $50,000, right? That should be a K up here too. I don't know why that K didn't come out. That's a K. All right. So this is the way that we state this, and of course, just symbolically, if we state this out, every time we state a null hypothesis, the null hypothesis comes in one and only one flavor. It says that the mean is equal to some value, mean 0, right? On the other hand, if we have our alternate hypothesis, we have our three choices. Either one, we call this a two-tailed test if the mean is not equal to that claimed mean. It's one-tailed. We call this a one-tailed test, a left-tail test, and we'll explain visually what that means. But we call it a left-tail test when the mean is less than that given value, and we call it a right-tail test if the mean is greater than that claimed value, right? If we're going for an alternate hypothesis. But we only have one way of stating the null hypothesis, but we have our choice right here for alternate hypothesis depending on what we're after. All right. And let's try another example right here. Let's say, what should we be saying about our null and alternate hypothesis based on the description? So here's this question. Study by researchers at the University of Maryland addressed the question of whether or not mean body temperature for humans is in fact 98.6 degrees Fahrenheit. Now, the results of the study by P. Mackwick et al. Appeared in an article called A Critical Appraisal of 98.6 degrees Fahrenheit of the Upper Limit of Normal Body Temperature and Other Legacies of Karl Reinhold August von Wunderlich. By the way, Karl Reinhold there, if you're wondering, was a medical genius, technically, of the 1800s who came to that 98.6 degree Fahrenheit number way back when, and that's just the number that has stuck with us. So among other data, the researchers obtained the body temperatures of 93 healthy humans. Let's suppose that you want to use the data to decide whether or not the mean body temperature of healthy humans differs from 98.6 degrees. How should we state our null and our alternate hypothesis? Well, let's read what it says right here. We want to decide whether the mean. So the claim right here seems to be that we're testing to see whether or not the mean temperature, body temperature in humans, is 98.6 degrees Fahrenheit. So that's our null hypothesis right there. We're going to say H0, the mean body temperature in the entire human population is 98.6 degrees Fahrenheit. And no matter what continent you live on, where you're at, who you are, that's it, right? Okay, so that's our claim, the null hypothesis. So what's our alternate claim? Now this one's a little bit trickier to read, right? Because we have those three choices. So let's say we want to decide whether the mean body temperature of healthy humans differs from 98.6. If we wanted to use, in a statement like this, if we wanted to use one of the two alternate hypotheses that says it's greater than or it's less than, you're actually going to see language in that statement that tells you whether or not it's greater than or less than. Since that isn't the case, right, we just say whether or not it differs, then our alternate hypothesis should be given as the mean is not equal to 98.6. So these are the two hypotheses we're testing, right? The null hypothesis, the mean body temperature is 98.6, versus the alternate hypothesis that it's not. All right, more to come.